the puja vacations. So this is it. And in this semester, I shall discuss atomic spectroscopy with you. Okay. So this is 902C most probably. So atomic spectroscopy is 50% of the paper. Okay. And rest part, molecular spectroscopy, will be taught by Surya sir. So I have already shared the syllabus here in WhatsApp group, routine also, and for books, I have given 2 books. Okay, one by Bransden and Joachim, Physics of Atoms and Molecules, and another is Atomic and Molecular Spectra by and also Laser by Rajkumar. Okay, so I have shared the PDF of both the books also. So you please download. Okay, and both the books are available in our departmental library also and main library also. So you can collect from there also hard copy if you want. Okay, and if you have any book from library you have taken during second semester, please do return the books to the library, and then at the same time you can issue for third semesters also. Okay, so you just update your departmental library account. Okay, so this is the information. So spectroscopy is one of the oldest branch of physics, and it mainly deals with the interactions of radiations with matter. Okay, and people believe that it started with the famous experiment by Sir Isaac Newton, where he showed that when white light passes through a prism, at the output light, a band of different colors. That means spectra is observed, and basically the lights get splitted based on the frequency or wavelength. Okay, so long back Newton did these experiments, and scientific community believed that this is the first systematic experiments to demonstrate spectroscopy, which deals with the interactions of radiation with matter. Okay. Normally, when you allow your any material or maybe gas or whatever may be with some kind of radiations, then what happen, uh, and if you see at the output through some spectrophotometer, you will see that a number of wavelengths, discrete wavelengths, okay, or corresponding to different wavelength or frequency. Okay, so each and these individual lines is known as spectral lines, or as a whole the whole system is known as spectrum. Okay, main uniqueness of this spectroscopy is that whenever you allow radiation to interact with any material, and if you observe the output, the outcome through some spectrophotometer or any other means, if you analyze, then you see that at the output, the spectrum, the wavelength or frequency of the spectrum is unique with respect to the material with which the light interacts. That means whenever you allow your radiation to interact with any molecule or atom or material, at the output you will have this spectrum or spectral lines. But the main issue is this frequency or wavelength of these spectral lines is independent, unique for each and every atom or molecule, or you can say material. That means if you have two material A and B, and if you allow a light or radiation to interact with A and B, and at the output, if you observe the spectrum, you will see that for these two different material, your observed spectrum or spectral line have different frequency or different wavelength. This property of spectroscopy allow scientific community to use spectroscopy as one of the important, very important diagnostic tool. For example, even when people are, say, synthesizing new material, say in chemistry, organic people, they synthesize new material. Okay, so there are several processes because there are some chemical reactions, and theoretically they know that if they follow this reaction, the output product should be like that. So how they will confirm it? Because you cannot see the structure visually. So they do a series of spectroscopy, say FTA spectroscopy, absorption spectroscopy, NMR spectroscopy. And NMR is very important for diagnostic of individual molecule. Okay, so spectroscopy is used almost all areas of sciences, even when the scientific community or in astrophysics, people send the satellite to different planets, they put some spectroscopic instrument inside the planet. Why? To do some spectroscopic experiments there. So there will be some source in the sense radiation source, and it will emit or radiate some kind of wavelength, electromagnetic radiations. It will interact with the surface of the planet. Okay, then after the interactions, the output, the spectrum or light received after the interactions will be analyzed to have idea about the structure. Okay, so every satellite, they put some kind of spectroscopic instrument there. So spectroscopy is very important. Okay, in science, it's a very older science and has enormous applications in almost all areas of sciences. So while you are designing your spectroscopy, so for example, say X-ray, this is also one kind of spectroscopy. So you allow your radiations having specific wavelength to fall on the human body or the material, and then you analyze the output. Okay, to have the it is give you the visual idea. Okay, so in spectroscopy, basically it deals with the interactions of radiations with matter, and at the output, at the end part, the resultant phenomena will be analyzed or measured. Okay, so there will, based on the analysis of the output or the radiations you are using to analyze your material or to interact with the material, there are several types of spectroscopy. Okay, so for example, if you allow your radiations to interact with the material, and at the output you measure the intensity of emitted radiations or absorbed radiation, then corresponding system is known as electromagnetic spectroscopy, that is absorption spectroscopy or emission spectroscopy, something like that. And it measures the intensity of the light emitted or absorbed by a system when it interacts with the radiations. Similarly, one can measure the vibration of the system when light interact with it. And depending on, one can have idea about the materials. Okay, so this is known as acoustic spectroscopy or dynamic mechanical spectroscopy, something like that. One can measure the energy of the associated with the particle when radiation falls on the material, and it can measure the energy gain or loss, something like that. And this is known as Auger electron spectroscopy or something like that. One can measure the mass when radiations interact with the material based on the wavelength or frequency and types of material. There may be ionizations and other phenomena. So one can measure the deviation in mass as well as charge, etc., and can calibrate to have idea about the systems. So this is known as mass spectroscopy. So based on the message is that based on the physical quantity you are analyzing at the output, when your radiation interact with the material, there are different types of spectroscopy. Okay, so there are different types of spectroscopy. So in our case here, we are mainly interested in atomic spectroscopy. Okay, so atomic spectroscopy means we allow radiations or electromagnetic radiations to interact with the atom of the material to have idea about the atomic structure. So atomic spectroscopy basically deals with the interactions of radiations with atoms. Why? To explore the atomic structure. So this is our interest. So we will, see this throughout this course. So this is our atomic spectroscopy. Okay. So according to atomic physics, if you go back to see different theories to analyze the atomic structure, you can recall that J.J. Thomson was a famous scientist who worked to describe the atomic structure, and he has given one model, and he suggested that mainly positive charge, because physically as a whole the atom is neutral, and at the same time electron is negatively charged, and so there should be some kind of something so that as a whole this negative charge of electron should be neutralized. Okay, so Thomson suggested that atoms are something like very similar to a current buns with electrons. Electrons means particles carrying negative charge, and positive charge is smeared across the bun, throughout the bun, so that as a whole this positive charge and the negative charge of electron neutralizes each other, resulting the neutrality of charge neutrality of the atom. Okay, so it's something like a sphere or bun where positive charge is smeared across the bun, and electrons are scattered or surrounding the bond. So as a whole, it's neutral. So this was some kind of uh, uh, acceptable theory, or one can say that first theory which was accepted to or can analyze the property of atom to a certain extent. At least the neutrality of atom having electron and positron can be analyzed. But after a few days in Rutherford's lab, two students, Geiger and Marsden, they visited Rutherford's lab. Okay, and Rutherford already, discovered the alpha ray few years back. So these two people, they went to Rutherford's lab and try to do some experiments where they allow the alpha particle to fall on thin metal foil. Okay, thin metal foil. These two scientists, Geiger and Marsden, they did the experiments in Rutherford's lab. So what they did, they allow alpha particle, and alpha particle was already known that time, to allow the alpha particle fall on the thin metal foil. And they observed some interesting results. Okay, they observed some interesting results. Most of the alpha particles, they found that travel across the foil without or hardly any deviations. Okay, but a small fraction, about 1 in 10,000, rebounded, okay, or came back to the initial incident directions. So Rutherford, after observing these results, analyzed that. So it's very surprising results if you consider the existing atomic model during that time. Existing model means Thomson's current bond model, where positive charge was spread over the whole atom. So if it is spread, then why a small part of the incident radiations get rebounded or come back? This is one issue. And so it gives some kind of confusion. So they started analyzing why this thing happened. So based on this experiments, Rutherford in 1911, he has given some kind of model to describe the atomic structure or property of the atom. Okay, so what he say is that inside the atom, the positive charge are concentrated in a very small part within the atom. And he said that maybe this part where positive charge is concentrated is about 10,000 times smaller than the atom, very small part. And say if you consider a small marble at the middle of a football stadium, so you can say that the marble is the a part where positive charge is concentrated. Okay, so and they assume that, and he assumed that this place or part where positive charge are concentrated is nucleus, and electrons are well outside the nucleus. Okay, And this idea was accepted very well as soon as he suggested. And the interesting or amazing fact to everyone is that you see, if you compare in an atom, you see that your whole positive charge is concentrated within a very small part, maybe 10,000 times smaller within the atom. That means most of the part of the atom is empty. Okay. And at the same time, almost all objects, including planets, human being, everything, material, are being made using some kind of atoms. So if you compare or analyze, one can say that most of the things within the physical observable are empty. So this was amazing. However, it was going good, but once stability of the atom, when people were analyzing the stability of atom, how atom is stable, because we know that the atom is stable and bound system. We know this thing. Now we need theory to explain this kind of thing. So Rutherford said that if all positive charges are confined within the center of the atom, known as nucleus, and electrons are outside the nucleus, well away from the nucleus, okay. So this was okay, but when one is interested in the stability, then how this can be explained? So this is because if you look into this structure, you see this is a very small structure, say an atom having, you see, 2 electrons. And this is maybe nucleus. So you see charge is plus 2e, and say electrons are, say, one is here and one is here, say. It could be here also, but for ease of analysis, we assume that here at the two end of the diameter, okay? So this is negatively charged, this is positively charged, this is again negatively charged. So there may exist repulsion between this electron and these electrons, and attraction between electron and nucleus. So if you analyze this force, you can see this attraction, force of attraction is 2 square q1 q2 by r square. So 2 square by r square. And repulsion, this is ee by 2e whole square. That means e square by 4r square. This is force of repulsion. So if you compare these two force, because since in the atom electrons are confined and it's a stable configuration, so always there should be a balance of interactions or force. So if you compare these two components, you can see that attraction is 8 times greater than the repulsion. Attraction is 8 times greater than the repulsion. So what we can conclude from this, that whatever Rutherford said, this is okay. It can explain several issues. But if we think about the stability of the atom, then we see that, say this, from this analysis, force of attraction between the electrons and nucleus dominates over the repulsion between this and this. So this means there is a high probability that electron should go and fall within the nucleus. But in principle, it is not occurring. It is not happening. This is stable system. Okay. So Rutherford, after this observation, Rutherford himself given some kind of addendum, I mean modification in his theory. So what he suggested that the like planetary systems, the electrons are revolving around the nucleus in such a way that this excess force of attractions is balanced out by the mechanical centrifugal force. While electrons revolving around the nucleus, they will feel some kind of centrifugal force outward to the radius. Okay, so this mechanical centrifugal force will balance this excess force of attraction, so that as a whole the whole atomic system is stable. Okay, so this was some kind of good. Everybody accepted the thing in a well manner. But again, after some times, people were analyzing about the stability of the system. Then scientists note down that according to Rutherford's model, nucleus is confined within the center of the atom. Electrons are revolving around the nucleus, and electrons are charged particles. So if it is revolving even in circular path, then there may be true probability of acceleration if direction changes or velocity changes. Okay, but here since it's in circular path, so its direction changes at every moment. It's across tangent. Okay, so it's some kind of accelerating systems, and by that time there was information according to Maxwell that accelerating charges radiate energy. That means if you have a system which is charged and at the same time accelerating, then it will radiate energy. So if it radiates energy, then what will happen? There is a probability that electron will lose energy with time. So if it is losing energy, that means force of attraction will dominate with time, and there will be a time when electron will fall down within the nucleus. So again, the stability of the nucleus or atom as a whole become a main concern. Okay, so there was a conclusion कि either Rutherford's atomic model is defective or our existing knowledge, because Rutherford's model is completely based on classical theory. So we can conclude that either Rutherford's model is defective, it needs modifications, or our existing knowledge of classical theory is unable to explain the atomic structure in a very good or proper way. Although Rutherford explained several features of the atom, and still today, Rutherford model is one of the very good acceptable theory which can explain several features of the atom. Although stability was a big concern according to his theory, he could not, satisfy the scientific community or explain the stable nature of the atom. Okay. So another scientist, Niels Bohr, he again went to Rutherford's lab for working few times. He observed this thing, and he also felt that if it rotates around the nucleus, being charged particle, it will radiate energy, and if it's continuously radiate energy, then what will happen? Of course, there is a probability that it will fall down the nucleus. So stability cannot be explained if it radiates energy continuously. So he suggested that instead of continuous radiations, he suggested that it can radiate in certain conditions, and it will radiate only in lumps or in quantized or in not continuously. Okay, and these lumps or amount are same as the Planck's quanta. So he suggested this. Okay, and based on his observations, or he suggested some kind of hypothesis, say number one. And what he did, he mainly used two things. One is he tried to use or apply Planck's theory, okay, and Planck's theory in Rutherford's theory. So he tried to combine two ideas, because Rutherford's theory was based on classical mechanics and Planck's system is quantum mechanics. It was quantized, so he applied quantum mechanics and classical mechanics simultaneously to explain the properties of atom. And it was observed that at the later part, his hypothesis is very good to explain several other features of the atom, which could not be explained using Rutherford's model. So he gave some postulates, and he said that electrons can move around nucleus in certain allowed energy states called orbit and not in others. That means it can rotate in certain allowed. There are some conditions, which electron can stay in which orbit, something like that. And the allowed orbit corresponds to definite stationary energy states. Stationary energy state means electrons will have some kind of stable energy. It will not radiate or absorb energy, okay, unless there is some external force. So these states where electron lie is stationary. So atoms is stable and it will not radiate. Again, he suggested that if electron jumps from one state to another, then there is a possibility of radiations or absorptions of energy. If it moves from lower to higher states, then it will take energy from the surroundings, and if opposite phenomena occurred, then it will radiate energy. So this is another postulate. And most importantly, he said that the angular momentum of the electron is quantized in a specific orbit, and this is equal to integral multiple of h by twice pi, that is mvr. If v is the velocity of rotations, then mvr is equal to nh by twice pi, where n is equal to 1, 2, 3, etc. So he used Planck's theory here. So analysis revealed that with the help of these postulates, one can have idea about several informations of atom. Okay, so first one can have idea about the radius of the electron orbit. So applying Bohr's theory, if let us consider an atom of Z atomic number, that means nucleus is having positive charge plus Jd, and Z number of electrons are rotating around the nucleus in their orbits. So using Coulomb's law, one can have electrostatic force of interactions between electron in a particular orbit and the nucleus, that is Ze E by R square. Here you see. So Z square by R square. This is force of attraction of a specific electron in an orbit with the nucleus, where R is the distance of the orbit from the nucleus where electron is lying. Again, since electrons is revolving, so there will be some kind of, mechanical centrifugal force mv square by r, if v is the velocity of revolution of electron and m is the mass. And in that case, this true force, that is z square by r square, must be equal to the centrifugal force towards the outward directions to have the stable configuration of the systems. So you see, since the system is stable, so mv square by r is equal to z square by r square. Again, according to Bohr's postulates, this quantized condition, that is mvr is equal to nh by 2s pi. So if one compare these two relations, one can have idea about r like this. R is equal to n square a square by 4 pi square m square by z, where z is equal to number of electrons in an atom. Say for hydrogen atom, z is equal to 1, or n is the number of orbit, like this. Say this is 1, 2, 3, 4, like this. So this is n is equal to. So if, say, you know the z, that means the atom you are discussing, and want to calculate the radius of nth orbit, there is first orbit, second orbit, third orbit, like that. So you put z is equal to the value corresponding to the atom, n is equal to the number of orbit, and you know the m, etc. So you can have idea, and E also you know, so H also you know, so you can have idea about the radius. So putting Z is equal to 1, that means for hydrogen atom, and N is equal to 1, that is for first orbit of the hydrogen atom, R is equal to this. So these H, pi, M, E, all values are known. So putting all these values, it has been observed that the value of the first orbit, this is known as Bohr orbit of hydrogen atom, is of the order of 0.5 to 9 into 10 to the minus 10 meter. And it was observed that this value is very close to the value of orbital radius of atom. And this is confirmed by kinetic theory of gas. So this is one success of Bohr's theory. Okay, so you can have idea about the radius. Similarly, energy of electron. If you apply Bohr's theory, you can have idea of the energy of electron in a particular orbit in a particular atom. So total energy is the sum of kinetic energy and potential energy. So kinetic energy is half mv square, potential energy is minus z square by r. If you consider an atom having z number of electrons, then electrons in an orbit having distance r, then the total energy is equal to half mv square kinetic energy minus z square by r potential energy. So total energy is like that. Okay. Now, say from here, mv square by r is equal to z square. Are comparing this equation with this, one can have E is equal to half z square by r minus z square by r. That is z is square by r. Again, we know the expression for r in terms of various constants here. So you put here value of r, so you can have an expression for energy of an electron in a particular orbit, something like that. E is equal to minus 2s pi square mz square e to the power 4 divided by n square h square. So n is the number of orbit where electron is lying, and Z is the number of electrons. So for a particular atom, for various orbits, if you put the value of Z and N and all other constants, you can have idea about the energy. Okay. For example, say if you take hydrogen atom and a hydrogen atom Z is equal to 1. So if you put N is equal to 1, that means in case of hydrogen atom, the energy for electron lying in the first orbit is minus 13.6 electron volt. How you do it? You put value of pi, m, z is equal to 1, e n is equal to 1 because we want to have for first orbit. H also So in electron volt, this is minus 13.6. Similarly, for second orbit, if you put n is equal to 2, then you will see that minus 3.4 electron volt. For next one, in this way, you can calculate by replacing n is equal to 1, 2, 3, 4, something like that. Okay. So if you put n is equal to infinity, infinity means it's outside the atom, because atom is something like that. Say this is your nucleus plus then first orbit, second orbit, third orbit, fourth orbit, something like that. Electrons are confined. Like say if hydrogen atom, that means one positive charge here, then one electron here. If say lithium in 3, so 3 positive charge here, so there will be 2, there will be 1. This is lithium. If sodium say 11, so 2, then you have 8, 8, then you have 1. In this way, electrons are distributed. There are other theory. Okay, how many electrons can have in a particular orbit? This is simple 2n square. Okay, 2n square where n is equal to 1, 2, 3, etc. So in this way, using this formula, you can calculate energy of these two electrons. Just putting n is equal to 1, and if it is sodium, then Z is equal to 11. If you want to calculate the energy of these electrons, okay, so you simply put n is equal to 2 and Z is equal to 11, because for sodium Z is equal to 11, then you can have. So similarly for hydrogen, Z is equal to 1, and simply putting n is equal to 1, 2, 3, 4, something like that. So you can calculate all the energies. Okay. So these are known as energy level diagram, where you horizontally put say lines, something like that. And for a particular atom, each line corresponds to a particular value of energy, from where this energy is related to the energy of electrons in different orbits of that atom. So for hydrogen atom, say minimum energy is minus 13.6 because n is equal to 1. So this is minus 13.6, then minus 3.4, putting n is equal to 2, then something like that, you can do it. Okay. So if you put n is equal to infinity, that means energy is equal to 0. So you see, in definite orbits, if electrons within the definite orbit existing, then always energy is less than 0. Energy is less than 0. Okay. That means electrons are bound within the system. If it crosses 0, then it will go out of the system atom, and we say that this is ionized. So this also gives some kind of idea about the bound system or stationary stable systems. And according to Bohr's theory, say hydrogen atom, you have one electron here. That means one electron having this energy. So if you give energy from outside, and if this energy is equal to the difference of these two energy, that means minus 3.4 minus 3.4 means 10.2 electron volt, then this will jump here. So again, you can supply energy, it will jump here. In this way, it can move, and at the same time, if it come back here, then it will radiate energy. Okay. So in this way, you can play according to Bohr's theory. It's possible, but if you supply energy, such that 0 minus 13.6 মানে is equal to হচ্ছে plus 13.6. Then your electron will go out of the atom. That means this is ionized. Or if your electrons just go to the higher level, from the level normally it is lying. For example, the hydrogen atom normally one electron in ground state. So if you supply energy, it will move upward. We say that this is excited. Okay, and the energy required to do that, we say that this is excitation potential. And you see the excitation potential is different for corresponding to different pair of energy levels. For example, if you want to excite electron from here to here and again from here to here, the excitation potential is different. Okay. So, and ionization potential, you are exciting electron from here to here. That means outside, you are making the electron free. So it will go out of the atom. So this is ionization energy. Okay. And if you know, when electrons are excited to higher level, normally lifetime of the electron in higher level is very less, of the order of -9 seconds, something like that, and it come back to the original states. And depending on this phenomena, how long it will stay, and during coming back, what will happen, there are several phenomena: fluorescence, phosphorescence, delayed fluorescence, so many issues are there. Okay, and these things have lot of applications also. Okay, so this is the thing. So when it's come back from higher level to original level, we say de-excitations. Okay, just opposite of the excitations. And the excitation potential corresponds to the ground level to the next higher level is known as resonance potential, or okay, resonance potential. So this is it. Again, one can have idea about the frequency. Because frequency corresponding to what? According to Bohr's theory, if you supply energy and if the energy is suitable, then atom will be excited. That means electron from one level to go to its higher level. This is known as excitations, and in that case, it will absorb some kind of energy, and again from higher level, if it is come back to the lower level, it will radiate some kind of energy. Okay, and this radiation corresponds to some wavelength or frequency. So Bohr's theory also give successfully idea of this radiation. That means frequency corresponding to these radiations or wavelength. So how one can do it? You see, let us consider an electron is excited from n is equal to 1 state to n is equal to 2 state. So already we know the energy of electron in different states. So say energy of electrons in n is equal to 1 is En1 and this is En2. Then the difference of these two energy, because you have to give energy, this amount of energy to excite from N1 to N2. And if you put it here simply, here, n is equal to 1 and 2, then and compare, you will have an expression like this. Okay, and again we know that E is equal to h nu. So if you divide this energy delta E divided by h, you will have the value of frequency delta E divided by h, because E is equal to h nu is equal to frequency. Okay, and in atomic spectroscopy, always we use wave number instead of frequency. And what is this? This is equal to nu by c. We write wave number as this nu bar is equal to nu by c. Okay, so this is wave number. So this is another unit we use. Just simply divide frequency by velocity of light. So in that case, wave number, that means frequency, if you multiply with c, you will have frequency. So wave number corresponding to a this absorption or emission, you can see is equal to delta E divided by hc. So this is equal to this. So easily you can have idea about the frequency. Again, this value, you see this is a constant, all pi m e h c. and Z is fixed for a particular atom. So replace this value using R. This is known as Rydberg constant, and this Rydberg constant is constant for a particular atom. And interestingly, in case of hydrogen atom, using Bohr's theory, because we have got this value R is equal to twice pi square mz square to the power 4 divided by h cube c using Bohr's theory. So if you put pi value of pi m z e h c in case of hydrogen atom, you know this all these values, then you see that this value is like that 109,737 centimeter inverse. Centimeter inverse because we have just divided by this one. C is below, so it's centimeter inverse. This is wave number. So, and interestingly, it has been observed that this value is close to the experimentally observed value of Rydberg constant for hydrogen atom. You see, this is the experimentally observed value of Rydberg constant for hydrogen atom. This value we got calculated using Bohr's theory, and this value we got from experiments. So you see this value very close to this value. So this is another success of Bohr's theory. So one can have idea, or Bohr's theory can successfully give you idea about the Rydberg constant. So this is another success. Again, Bohr's theory can successfully give idea about the hydrogen atom spectra. Hydrogen, this is simple because already we have seen that from this analysis, during emission absorption, Bohr's theory can give idea about the frequency or wavelength corresponding to this absorption and emission. So Bohr's theory, if you apply in case of hydrogen atom, you see, say in case of hydrogen atom, one electron is there in the ground state. So if you supply energy, it will be excited from n is equal to 1 to 2, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5. In this way, you can excite. Then again, it will come back to previous states. Okay. So say if you are exciting, initially your electron was here. It's without, unexcited conditions. So you are excited it, say very high level, so it will come back. So during this return, if you consider all the lines corresponding to the return from higher level to n is equal to 1, you see it can come from n is equal to 2 to n is equal to 1, 3 to 1, 4 to 1 in this way. So this is a series. This is known as Lyman series because Lyman is a scientist who first explained these things, and they can use Bohr's theory to calculate exactly the wavelength or frequency corresponding to these lines. Then if excited electrons comes from higher level to n is equal to 2, that means from 3 to 2, 4 to 2, this kind of things. So this is known as Balmer series. And this is the first Balmer line, then second Balmer line, third Balmer line in this way. So here also first Lyman line, second line in this way. So if electrons come from higher level to n is equal to 3, this is known as Paschen series because Paschen analyzes this. Then bracket, he analyzes this. So in this way, they analyze this, and all these scientists use Bohr's theory to calculate the frequency or spectra, frequency corresponding to these lines. And interestingly, it has been observed that the calculated value well match with the experimental value. So Bohr's theory successfully able to analyze the spectral lines of hydrogen atom. Okay. So this is another success of Bohr's theory. There are some limitations of Bohr's theory, but before discussing the limitations, today I will stop here, and to next class again we will continue with some more discussion on the success. Then we will discuss the limitations and how this can be analyzed. We will see. Okay. So message is that Bohr's theory, Rutherford theory is a very good, fast, concrete theory. Still, people are using to analyze several features of atoms in a proper way. This is very good. However, stability was a very high concern in case of Rutherford theory. Bohr's theory was successfully, capable of giving idea about the stable nature of the atomic systems. Using Bohr's theory, one can have idea about the radius of orbits where electrons is lying. It can give idea about the energy of electrons in a particular orbit. It can give idea about the frequency or length when electrons jump from one level to another during absorption or emission. So, and also it can give idea about the Rydberg constant in a very proper way, which is very close to the experimental value. So all these are the success of Bohr's theory. Okay. So another issue, you see, according to Bohr's theory, in a particular orbit, you see, we know that 2n square number of electron can stay. So here 2 electron, here 8. According to Bohr's theory, all these electrons will have same energy. That means degenerate. Okay. Here also it's 2 electrons have same energy, degenerate. Okay. But experimental observations show that these are all, these are not degenerate. Okay. So we need modifications in the theories to have exact explanation. So we will see it later. Okay. So next class, what we will do? First, we will see some more success. Then we will discuss about the limitations, and then we'll go. Proceed further. Okay. So if you have any questions, you can ask me, or you can go through, and then we can discuss also. So Uma,
Yes,
you
sir.
want to ask something or say something?
No, sir, I have no query about this.
So you?
No, sir, I have no questions or no query
Oh,
about
okay. Okay, okay. Then Nitul Sharma,
Yes, sir.
would you like to ask something?
No, sir.
Okay, so then if there is no questions, I am closing this session here. Next class we will discuss, and most of the notes are given in this portal, so you can download it from there, or you can directly download from my website also. Okay, so I will share the link here, and you follow the 2 books I have shared with you, the PDF. Okay, hard copy also. You can follow other books also, no problem. Okay, so okay then, bye.